Alejandro, thank you so much for joining us. If those on the call are surprised to see you, I knew last night that you would be our guest, and that Rachel had nominated you when she realized that she had a conflict. But we're very, very appreciative that you could join us. And her handoff last night talked about your involvement with, I think, one project in particular, timber construction. But you have a very interesting background, and you could probably describe it better than I can just in looking at your LinkedIn profile. We've never met, with training both in architecture and engineering in three different incredible institutions in three different countries. Work in a city I know a little bit, Poitiers, and we could talk about that at some point also, over maybe if not a beer, a glass of wine. But do you want to introduce yourself and why Rachel thought it was important that you represent the office?
Yeah, absolutely. Well, thank you for having me here, actually. Yeah, so my name is Alejandro
Could
Fernandez.
I just interrupt? Is it okay to be recording? I don't think we'll be talking about anything too controversial.
Please go ahead.
There's several students who are traveling. It's our vacation week, and it'll allow them to hear your presentation subsequently.
No worries at all.
Thank you.
And also, I don't know what you guys see on my camera. We're trying a new camera, so I don't know if, hopefully you can see me okay. But,
yep.
So, yeah, my name is Alejandro Fernandez. I'm actually from Madrid, Spain. So I'm happy to hear that you guys did another of these virtual field trips to Madrid a few months ago.
Yes.
Yeah, I studied civil engineering there with a focus on structures. While I was studying there, I got into a double degree program with an engineering school in Paris, in France. And I did another master's with a focus on structures in Paris. While I was working there, studying there, I did my thesis project on, it's actually the way they do it is you actually go do real work. So I was working in RFR, which is, you guys may be familiar with, or you have heard about Peter Rice. He created this office when collaborating with Richard Rogers and Renzo Piano and others doing the Pompidou Center. So it's a firm that has kept his memory alive. And in there I was doing mostly bridges. And that's the Poitiers viaduct that you mentioned, Rick. And once I finished, I thought I wanted to change my my career, and then I wanted to become an architect. So I came here to Chicago to study architecture. And after I finished my master, I was practicing for a brief period, and then I got an opportunity to join TT. And I had always been fascinated by the towers and the big buildings they do. And I got an opportunity to join the team. So that's what I do right now. And you can probably guys see behind me some of our towers, some of the projects we do here in the office. Now, here in TT, I've been working in different number of towers in a different number of countries. And a few years ago, I got an opportunity to work on a research project for a mass timber building in here in Chicago with Perkins Will and the University of Cambridge. So we thought maybe we could present you guys the work that we did there. And that work was very important because it helped us get started with another project that we just topped out in Milwaukee, and which has become the tallest mass timber building in the world. So even if the project here in Chicago never happened, it was more a research project. Right now, it has developed this other project that is becoming a symbol of mass timber construction for other places. So, Rick, I think, is that a
Yeah,
good enough introduction?
that's a great introduction, and you should have the right to share screen. But could I just picking up on one aspect of your introduction? I just checked dates on the on your LinkedIn profile and that of a good friend of mine, also an engineer who worked at RFR at the same time as you. Up until September of 2011, you both left. Sophie Pennetier. Did you overlap at all with Sophie?
Was he on facades, maybe?
Yeah, on facades.
Yeah. Okay. Okay.
And she's now at Enclo in Los Angeles and hosted us there in a prior iteration of the field study when we could actually travel before. She came to New York to do an exhibition at the Center for Architecture called Liquid Wall for RFR, and then eventually stayed on and worked with Guy Nordenson and others. But I won't digress. The floor is yours for the presentation, but we've kept in touch.
Funny, yeah. We barely knew each other because it was like different parts of the company, but funny concept. The world is too small.
Very small world. Yep.
Okay, so maybe let me share my screen. Okay, can you guys see the presentation?
Almost. It says you've started screen sharing. There it comes. Excellent.
Let's give it a second. My computer's a little bit slow this morning.
Do you want to make it full screen? We see the title slide and the, great.
Here we go.
Perfect.
Okay. So I thought this image would be a good image since you guys are focused on Chicago to start. This is the, try to get my, so this is the building that I was mentioning, this mass timber high rise that we proposed for the city of Chicago. And just to give you a little bit of where we are, where I am right now, and you may have seen it in the 3D view in my camera, but we are, this behind here, I believe is the top of, where is it? I don't see Trump Tower, but if the river goes here, it probably turns around. So I think, yeah, you can see it almost here. This is Trump Tower behind the Willis Tower. And this is Mies van der Rohe building, I believe, down here. And that's where our Chicago TT office is. And that's where I'm talking to you from. So we've already gone through the introduction. So I want to make sure you guys had a brief idea of what is mass timber first, but then we'll talk a little bit about River Beech and the new project that I mentioned that is the current tallest in the world. And the reason why people are focusing right now, there's a lot of reasons for mass timber, including, it's not a small one, like the current rise of on construction materials. Like right now prices are skyrocketing, and there's a huge escalation on prices. So having other materials is always great, but also in the context of meeting the targets that the architecture and construction industry have target ourselves, and trying to reduce the amount of CO2 emissions in the planet. Wood is an incredible material because not only it has its fabrication process has smaller emissions than traditional materials such as steel, brick, or concrete, but it actually captures CO2 during construction. And there may be some discussions about when this CO2 is going to be released, but as an industry right now, we have established some very short targets for 2040. So having tools that help us achieve these short-term goals are incredibly important. Having this as part of the structure, it's also very important because when you look at the total embodied carbon in a building, about 45% or sorry, about 70% of it is actually embedded in the structure. So if we are able to reduce these these very large numbers, that's a huge success. Now, just in case you guys are not familiar with mass timber, what I'm talking here are products that are composed of laminations of different sizes of timber. So traditional timber construction is more like stick framing, which is 2x4s, 2x6, 2x8s, and they are nailed together to form like houses. Now, when we're talking about mass timber, we're actually taking these pieces of timber and gluing them together or nailing them together, or mechanically joining them together to create these bigger pieces. Now, because we're creating bigger either columns, beams, or slabs, the performance of this material is very different from what we're used to on traditional timber construction. And then we can achieve buildings that are bigger than what would be allowed by traditional timber construction. Here's an example of how we are building that. It's actually not technically mass timber, but we think it's an interesting. This is a Wisconsin manufacturer that just harvests full buildings and creates the structure out of a single tree member. Now, mostly today, I'll be showing you images of glulam beams and CLT slab. So glulam beams is glulam beams or columns. You basically just stack them in one direction, one on top of the other. It's about 1.5 inch laminations, and they are stacked on top of each other. In the CLT, what we do is we cross them 90 degrees between layers. What you do by doing that is you first get like a second wave behavior, but it also, wood tends to shrink over time. By creating this, and wood doesn't shrink too much in the direction of the fibers, but it changes volume more significantly in the direction perpendicular to the fibers. So by creating this secondary layer perpendicular to the main layers, then we're able to constrain those movements that are natural on wood. And just to show you a few images of what is possible with wood, there are like different systems that are currently being utilized. We have things that are like post and beam construction, where you have like a glulam column with glulam beams on top, and then you have the CLT slabs above. You can introduce a girder and just have like joists, so you can have your beams more closely spaced, and the CLT slab becomes smaller. Or you can actually remove all the beams and just have the CLT supported on top of the columns. Now, when you're doing that, you're gonna end up with columns very closely spaced. So different buildings will require different things. You can also use your CLT as walls, and not only as floors, but also as walls, and just bear on these CLT walls. This is pretty typical in Europe, perhaps not so much here in the States for now, but you'll see it will happen more and more. And then there is like a mix between old and new, which is stick framing. So it's using these traditional stick elements, and then just using the CLT for the floors. So all this would be concealed in gypsum, but the CLT gets exposed. And now we're seeing a trend, which is mixing materials. So you can either mix it with steel or you can mix it with concrete. And especially as we go into taller buildings, it may start making sense. Now, probably all of you, at some point or another, will think like, okay, we're going to be doing harvest with timber, but timber burns. So how is this possible? Well, what happens with timber is actually very interesting compared with other materials, especially when compared with steel. Steel, when it heats, it transfers the heat through the whole area of the section, and then once you achieve a certain temperature, you lose completely the capacity. And this image from above here is from an old building where there was a fire, and you can see how the timber element resisted, but the steel lost all its capacity. Now, the magic thing with timber is that it creates this char layer on the exterior. And by creating this char on the exterior, the char protects the interior. So in the interior of the element, you keep your properties, your structural properties almost untouched. And then all you have to do is understand how long the fire is going to be, or for how long do you want your protection to be. And you just make sure you have enough wood around the structural part that you need for the fire case to sustain the loads. So, and that's something that is very well known. And for example, we know that during a 1 hour fire, the fire advances 1.8 inches an hour, and then you have a 2 hour fire, it's more like 2.6 inches an hour, sorry, like 1.6 inches an hour. So it's all codified and well known. And you can see here like how like the connections, if you do it properly, you can embed your connections inside of the timber element, and then the exterior will get burned, but your connections remain intact. So this is the magic that we're using for all this new building. So going back to Chicago now, how this became possible. So right now in the or before, this is going back to 2017, where the tallest mass timber building in the US was 7 stories tall. In Europe, they had taller buildings, probably more like in the range of 12, 14 stories back in that moment. And University of Cambridge, they had a significant amount of funding, and they were trying to figure out where to use that funding for. So what they did is they reached a number of architectural and structural companies, and they asked us to design high-rise mass timber buildings, trying not with the target of building these buildings, but more to explore the possibilities of the material, but most importantly, to identify where the limits of the technology were at the time. So that's why they asked us to design this 800 feet tall, 80-story mass timber building. Perkins and Will at the time, they were working on the development of all these lots around the river. This is like the south part of Chicago. So we decided, okay, we'll use that site as our case study, and we'll develop this building over there. Now, to understand to pick a case study, we start with a traditional building where you have a corridor in the center and you have units on both sides. Now, structurally, the most efficient thing you can do is always put the structure on the exterior of the building to resist the wind forces, which is what becomes controlling for a tall building. So if you're doing a small building, then your columns, where your columns are, where your walls are, that's the important part. Once you go into all these very tall buildings, the big concern always is, how am I going to resist all the wind forces? How am I going to resist the seismic forces? We're in Chicago, so actually we don't have significant seismic forces, but as you know, Chicago is the windy city, so wind is a very big concern up here. So if you're trying to have the most efficient structure, then what you want to do is actually you want to push the building out. So not only we push the facade to the structure to the facade of the building, but we actually split the two units into two different buildings on an aim to gain on the depth of our system and make it more efficient. Then at that point, we had kind of like a diagram system, and we were discussing with the architect, okay, architecture, you want to maximize the views, you want to create like very rectangular openings. However, for forces, it's hard to flow around a corner. And when designing with a material, it's very important to understand how does the material work better. Wood connections are very easy to do when you're trying to do axial forces, when you're trying to push one piece against the other. But it's much harder when you're trying to transfer bending through the connection. So what we did is we actually diagonalize all our diagrid to simplify our connections, and we have like a much more efficient structure. And through multiple iterations, we ended up with the building on the right, which had 2 towers with a diagrid on the facades. The diagrid is was conceived as a LVL, laminated veneer lumber. So basically, you peel a trunk and you glue the laminations to each other, and then each of the 2 bars of the building was joined by a glulam diagrid in the middle. So at the end, you can imagine this building bending, and when it bends, the diagrid gets engaged and transfer the forces from one building to the other, creating a very efficient. Now, the other thing that the diagrid gave us is wood. It's a great material, but compared with the steel or concrete, its capacity is smaller. So once you go into a very tall building, you may end up with like very large column sizes. Now, by creating this diagrid, we were able to create like this, distribute all that area that we needed to support the building into many different members. So each of these become like a smaller column that at the end becomes in total becomes a large area of wood, but it doesn't have a big impact on the architecture of the building. So if I give you some architectural renders from Perkins and Will, you can see here the 2 buildings with that intermediate space. Now, what that intermediate space allowed us was to create a great atrium for public functions. You can see the diagrid view from below with some intermediate spaces. That's another advantage of the diagrid, is because you have like all these members, you're gonna start creating openings because the diagrid will just like transfer the forces around it through all the members. And here are these atriums that were created in the interior, and you can see that the beautiness, right, of these atriums, like having the wood exposed. It really creates a very unique space, very different from what we're used to. Another image of the atrium, and then the spaces within the unit, and this idea that you really feel in a natural environment. I don't know if you guys have had a chance to walk into a mass timber building, but it's actually one very common reaction when you go into a mass timber building is the first thing you want to do is touch a column, touch a wall, whatever you can to experience this member, this environment, and it's very unique. So you see some more images. Now, the other advantage of mass timber is allows for a lot of prefabrication, and its weight is 1/3 of the weight of concrete. So it's the prefabricated elements can be much. You can prefabricate much larger elements. So one key thing of this project also was to define how like these modules were going to be fabricated offsite, and they were going to be brought into the tower. So if you can imagine one of these units, it's probably built out of 2 different modules, and then each of the modules is fabricated outside of Chicago. It's brought in a part, so a very efficient transport system. And because we were next to the river, these pieces could be picked and then dropped into the building. So, at a nutshell, that was the River Beech project. Now, what I wanted to take the opportunity to show you too is what that allow us, because when back in 2017 we published on CTVUH journal the results of this research, and it went into Arts Daily and a lot of publications. It had a lot of noise. I was actually very surprised of all the we started getting like people asking for interviews, and I was very surprised because it was a research project. But what I realized at the time is what this project is, it showcased the possibilities of mass timber. Now, there was about 2 hours north of Chicago is Milwaukee. In Milwaukee, there was this developer. It's self-made developer, immigrant himself, that built his own company, started as a painter, and now he's like building all these buildings in Milwaukee. And they had owned a plot of land in downtown Milwaukee, and where they have like tried to build a 35-story tower. They had the zoning approved, everything was going great, but they couldn't make the numbers work. Like, even if in Milwaukee, concrete is actually very cheap, the numbers wouldn't work. They couldn't figure out how they were gonna sell this building. Now, when they saw the thing that we're doing in Chicago with River Beech, they called us and they said, hey, could we do something, maybe not as crazy, but could we do something similar here? At the time, they wanted to do an 18-story building. So as you can imagine, coming from 18, we were like, yeah, absolutely, let's do it. And this is how Ascent started. Today, Ascent is actually a 25-story building. It grew up over the design process and gained an extra 7 stories. But it's currently the tallest mass timber building in the world. It consists of a concrete podium, which is parking, with a mass timber residential building above, and then an amenity area on the top of the building. And you may say, okay, yeah, but you're using concrete. Well, you want to use the right material for the right place. For the parking, for example, we're in Milwaukee, we have like heavy snow, we have like all the salts for all the de-icing salts. You don't really want to have all the salts into your timber, and you don't want to have the cars rolling on top of all that. So we have the podium is concrete, and then once we transition into the residential area, that's where we go into the mass timber. Here you can see some of the floor plans, the typical parking on the left, and then in the middle is the typical residential level, where we have like 2 concrete cores, and then a corridor joining them, and then the units at both sides of the corridor. And having these cores, actually, it was an important thing, because we, at the time, so this project started about 2018, and at the time, the tallest building in North America was 9 stories. So one of the first things we had to do was go and talk to the city and tell them, hey, we want to do an 18 stories building. Would you let us do it? And one of the ways we had to convince the city was to tell them, okay, we're gonna do all the columns and the slabs in timber, but we're gonna keep the cores built in concrete. So the lateral system of the building will be these 2 cores. You will have all your stair egress, your egress stairs and communication path for both evacuation of the building and for the firefighters to get into the building. And all these areas of safety are enclosed in concrete, which is a very well-known material for which we know the performance. And finally, on this slide, just the top of the building. This is branded as a luxury building. So they have a very top-notch amenities on the top of the building. And here are some images of what the building is going to become. And I'll show you some images of construction at the end. But you can see here that for the owner, it was very important to keep the timber exposed. And this is something that at the time was fairly innovative, because no one had ever done a building this tall, keeping the timber exposed. There was a precedent in Canada of a dorm building where they had also built in mass timber, but all the timber was concealed in gypsum. So the gypsum, the plaster boards were protecting the excuse me, the structural elements. But for the owner, he told us, like, look, if I'm gonna cover my timber, there is no sense. So making sure all the timber was exposed was very important for this project. So here you can see a summary of the structure, and you can see the podium with the two cores, and then a grid of glulam beams and columns, and then the CLT slabs. And if we look at the typical floor, you can see the beams, the typical span north-south. We have like some secondary framing for some balconies over here, but most of the beams span north-south, and then the CLT spans perpendicular to these beams. And then this is something interesting and good to know, that timber, you can do long spans, but because timber is a softer material, it has more deflections. So if you want to do a longer element, you require very big members. So in order to keep the floor to floor at a decent size, at a very reasonable number, we kept the columns fairly close to space. Like these columns are 20 to 25 feet of space in the north-south direction, about 16.5 to 20 feet on the east-west direction. So you end up with a fairly dense grid of columns. Now, this doesn't really work once you go into a parking level where you need to have your drive aisles, or if you go into retail area, lobby areas where you need to have like bigger spaces. So what we did is at the top of this podium, concrete podium, we have a system of PT girders that transfer the loads from these columns back into the concrete grid. The concrete parking, but maybe not very important. And hopefully this goes okay in your computers. But here you can see a quick animation of the building. And what you're going to see is the construction. So as Milwaukee, we have to go with very deep foundations. We start building the concrete podium first. And then once we get to this top of the podium, we have this transfer area with these PT beams. And then once that was finished, we start like bringing all the glulam. So you have like all the glulam columns and beams. And as the beams and columns are erected, we start dropping the CLT floors. And it's literally that. We just drop the floors. And then the construction continues. And back in December of 2021, we topped the building, and right now the whole building, the whole structure is finished. They are progressing with the facade is almost at the top, and they are progressing with the interior with all the interiors. So just to show you a couple connections, so you see how like these pieces connect to each other. The simplest thing you can do is just have like a beam on top of a column and just like have them bearing on top of each other. This is a very efficient connection. But this is for the fire ratings that we were asked on this building. It was hard to do for areas that were living exposed. So we did this whenever we had like bathrooms, kitchens, or areas where we wanted to conceal the timber in gypsum to protect it from water or from grease or from other damages. So that actually is interesting. About 50% of the building ends up being encapsulated in gypsum, not for structural reasons, but just because the use of the building requires to encapsulate this timber. Now, where we were able to explore the connections, we use this connection. It's just a simple steel angle that gets screwed into the column, and then the beam. You can almost see it here. It's notch, so you just drop the beam on top of the steel angle, and then at the bottom we introduce a block after the fact to close the connection, and at that point all this steel connection becomes completely wrapped in wood. So what we're doing is we're protecting the steel with wood, and we design based on that char layer that we mentioned earlier. That's the fire protection of this connection. And then this is just to give you an idea of how like the floors look when they come into site. Is this long slabs or floor panels that are about, in the case of Ascent, they are about 7.5 foot wide, 40 feet long, and then 7 inches thick. And then 7 meters of construction. Here you can see like how these CLT panels, they are hung. So what they do is they put some temporary connections at the top of the panel. Then they just hang it and drop it in place. The crew is very limited. It's a crew of about 10 people working on this building, on the timber areas, and they are able to erect 1 floor per week, which is very quick, because you guys don't realize, but it's a very quick erection process. The workers love it because it's a very clean construction technique. They don't have to get dirty with concrete. They don't have to be carrying heavy reinforcement bars. So they actually love it, and it's also a very clean site. You can see here we haven't cleaned we didn't clean the floor for this picture. There is not that much extra material. All you get here is some dust from the timber if any cuts need to be made, but everything is pre-engineered. So all the cuts come from the factory. Even like the penetrations for the MEP come pre-drilled from the factory. So all they have to do is just enter one piece into the other, and that's it. Here you can see some of these hangers for the CLT. This is what they put on top of the CLT. And then here you see like all the holes for the MEP. Now, one thing that it's very important with a mass timber building is to be able to seal it. So we, as you can see, nothing is protected the timber. So if it rains, the timber gets wet, which is fine. But all you want to do is you want to make sure that you seal the joints very well. So if there is water, the water only stains the top of the panel. And something maybe I haven't mentioned yet is that these 7-inch CLT panels, they are covered by a 2-inch gypcrete topping. The gypcrete is like a cheap concrete. So even if the water stains the top of the panel, it doesn't matter because it's all gonna get covered with this topping. Now, you see here the size of these columns. They get fairly decent at the bottom, and this building was only supporting 18 stories of mass timber. So if you think, going back to River Beech, where we were talking about 80 stories of mass timber, you're trying to support 80 stories on traditional columns, the size of your columns would get huge. So that's why it was very important to have that diagram that allow us to distribute the amount of timber that we actually needed to support the building, but we were distributing it over many members, so the size of each of these members was smaller. And then these are some pictures from a few months ago, also during construction. So you see that at this point, the concrete was already erected. And then they were starting to assemble the facade on the exterior, and then all the mass timber was going up. And that's what I had for you guys today. I mean, I could keep talking about this for a very, very long time, but I wanted to give you guys some time to chat and discuss.
Chichis, I see you have your hand up.
Yeah. So what about the durability and life cycle cost of the buildings built by using mass timber technology? Durability in terms of lifespan.
Sorry, are you asking about the lifespan of these buildings?
Yeah, durability in terms of lifespan.
Yeah. So, this is a great question. And one thing that when we are asked this question, I always think about like old churches or like all these Chinese pagodas that have stood there for hundreds and hundreds of years. So the timber actually doesn't behave very bad if you keep the humidity or like the water out of it. It behaves very well. What it really damages timber is if you have like you wet it and then you dry it and you wet it again, that becomes an issue. So in the case of Ascent, all the timber was concealed within the facade, so we don't have exposed timber, and yeah, we don't have many durability concerns right now. Also, if you think about buildings, the cycle of buildings that we design for is typically 50 years, maybe 100 years, which doesn't mean that we need to think that the building is going to be demolished in that time. We should design buildings to live forever, but I don't think durability is a big issue for mass timber.
So basically, it means that it is not suitable for tropical regions, this technology.
For tropical regions, I think you can do it. Like, for example, right now we're building a canopy in Tennessee, and it's going to be a beautiful, actually with our friends from Studio Gun that you guys talk with, and this canopy is going to be completely exterior. Now, once you're going to do that, then you have to do treatment on the wood. So in the case of that canopy, we're like pressure treating the wood. So you basically put the wood pieces into a chamber and then treat the pieces so they don't absorb that humidity that they're going to be exposed to. So you can do it. You just need to be careful and design for it.
Thank you. Thank you.
Daria, I see your hand is up.
Yes, thank you, Professor. And thank you, Mr. Alejandro. Could you hear me?
Yeah, I can hear.
Yeah, just quick questions about how to ensure that you achieve the desired strength of the wood. I mean, like when you're designing the wood, you have to know about the strength, particularly in bending on compressions, and how did you achieve that? That's all. Thank you.
Yep. So I think that has two different components. One thing is like all the wood strengths are codified. So wood is something that we've been using for a very long time. So there is like codes specific for wood that tells you the strength of the wood for its different species. So actually that's something that not many people realize, but when you're designing with wood, you have to understand that spruce is not going to be the same as Douglas fir or southern pine. So in the case of Ascent, for example, we're using European spruce, which is good for bending. It's a little bit stronger in bending, but it's very, if you crush it perpendicular to the grain, it doesn't have much strength. But all that is codified. The one thing that is interesting with a natural material as timber is that it has natural defects, right? You have knots, you have, so what they do when they develop the codes and they develop these properties is they add a safety factor on the properties that they test on the material to make sure that we understand all those defects and we're able to, even if there is a small defect like a knot in the material, your column is still gonna have the resistance. So you kind like over design it in a way.
Thank you.
Sure.
I I also wanted to add my thanks, Alejandro. It was a great presentation. And I have to admit, I wasn't familiar with the project in Milwaukee. I was looking at the Perkins and Will collaboration of your firm in Chicago and saying, you know, what were the impediments, regulatory and otherwise, that prevented that from happening in Chicago, the city, you know, known as the Windy City, but also known for the Great Fire, which precipitated the massive use of masonry instead of wood in Chicago. Milwaukee is not far away from Chicago for those who haven't been there, but a different culture. And I shared with everyone the article that Nadine posted by email that Nadine Post wrote in ENR in December of 2020 about your firm and this project, because it corroborates exactly what you've been saying about the cultural differences and the willingness of people in Milwaukee to be more adventuresome, at least in terms of, you know, using a traditional material in a new way, a new material, if you will. And what came across in your presentation and in Nadine's article was the degree to which there was a negotiation, you know, with code officials, you know, the testing that was done, the burn test that your firm coordinated, but also, you know, compromises over the stairwells that you showed, the use of concrete in the stairwells and the standpipe systems. How was it, in your experience, in your firm's experience, that Milwaukee could happen, Portland could not, Chicago, New York hasn't happened? Is it that fire department officials or building officials are just so overly cautious, despite the evidence that, you know, fire resistance isn't the issue, that you know, if life safety is paramount, it's not a problem. In many ways, it could be safer, you know, because of the massiveness of mass timber, tautologically. You know, what were the lessons learned, if you will? And I'll just, you know, say one other thing that I saw in the article, which surprised me. One of the developers, Tim Gockman from Newland, was quoted as saying, "Had we known all the challenges at the outset, we probably would not have started." And I was also heartened to learn that he or his father are Ukrainian immigrants to Milwaukee, and this building, which will be the tallest mass timber construction in the world, correct? Yes. When finished, is a phenomenal testimony to, you know, immigrant energy and entrepreneurship. So I don't know. There's a question in there somewhere. You know, how could this happen other places than Milwaukee?
Yeah, no, absolutely. I think we got fairly lucky in Milwaukee, in the sense that the commissioner at the time, he had a background in forestry. So Milwaukee, Wisconsin in general, it's been this wood supply, the timber supply for Chicago for centuries, right? Like timber would be cut in Green Bay, and then they would transport it by boat, and then it would be cut in Chicago. It would be used for Chicago, and then it would also be distributed through the Midwest after being produced in Chicago. So they understood. First, he had a background in forestry. They also understood the opportunity for Wisconsin and Milwaukee to be doing a building of this magnitude that is like, it showcases the city, it showcases the energy of the city. So they were very supportive from the beginning. They were also very well informed. So we talked with the city first. That was our first step, like talking with them, making sure they were fine doing the building. The second meeting we had was with the fire department. Because we wanted to make sure they felt comfortable doing this building, and we wanted to understand what concerns they may have. Actually, one of the big concerns wasn't so much about fire itself. It was more about the smoke, how to control the smoke, and how to make sure that the smoke didn't go through those joints between the different timber elements. So that's what we had a negotiation with them about, like, what elements could we give to prove that the performance of the building was similar to other buildings that are being done right now of similar heights. Now, that said, since we built this building, the code has changed a lot. And right now, there's been a lot of testing of mass timber in different parts. And the new edition, so for your students, I'm sure you're familiar with it, but for your student more than anything, most jurisdictions here in the US utilize the International Building Code, which is, it says international, but it's mostly developed here in the States and used in the United States. And that's the basis for our buildings. And it tells you what you can do and you cannot do. In the 2021 edition of the code, 2015 was the first edition where they adopted mass timber, and now you can use CLT, but they were only allowing you to do up to 8 stories. In the latest version of the code that was adopted in 2021, in that version, they now allow to do up to 18-story mass timber buildings. So I think that's a big game changer in the sense that cities all around the country are going to start allowing for these buildings. And you can imagine after doing this building in Milwaukee, we're right now in conversations with cities all around the country trying to do this. And there is like an insane amount of projects. Like pretty much every architect right now and every developer wants to have a mass timber option, and then they'll see if it's possible. But there is a lot of buildings, and it's actually growing a lot. And we're seeing that cities are not, I suppose, maybe cities like Chicago are a little bit more restrictive, but Boston, they just launched a program for mass timber buildings. New York, I think they are adopting also some provision to start allowing mass timber buildings. So it may not be as tall, it may be a little bit more limited, but step by step, I think like cities are growing higher. So I think we're in the right path, and I think people are starting to get convinced that this is possible. Not only is possible, but it's safe to do. Like we're not, there is testing, and there is like things that are put in place to make sure the safety is similar to other buildings.
It wasn't a tall building, but it was large. I was fortunate enough to see Sibelius Hall in Finland, in Lahti, north of Helsinki. I was actually traveling with Jeannie Gang to Jyväskylä, and we were able to see this incredible mass timber concert hall that's been there for almost 20 years that could hold 1,100 people. And the people in charge of the construction were saying it was in many ways safer than a building made of steel or concrete. But again, as you say, like Milwaukee, Finland is heavily forested, and it was a natural outgrowth, even the national epic. I have one more question, and I really appreciate, especially with no advance notice, you're jumping in to represent the firm and bring these projects to our attention. We've been talking with just about everyone in New York, but also during this field study about supply chain issues. And, we've been hearing about, increased cost of wood products, especially here in New York in general, but also about how difficult it has been to get steel. And a lot of discussion about alternative formulations of concrete for environmental reasons. And obviously mass timber, on an environmental basis is at the top of the list of any possible alternative. But coming back to supply chain, was there any impact at all in terms of Ascent or other things that are maybe in the offing about either the cost of wood products or the availability?
Yeah. So one thing we did for Ascent is we designed when we first started the project, and it's back to the question of your student of timber properties, we designed it for American wood properties. And once we went out in the market, we noticed there was a lot of fluctuation, right? There's a lot of prices. Right now, there's a lot of stick framing construction in the US, but there isn't so much mass timber manufacturers. There's a limited number of manufacturers with limited amount of production. At the time, we also had Trump imposing all the sanctions on Canada, so that also helped drive the prices up. So then we started looking into Europe. Now, the thing with Europe is we we right now see mass timber as something very innovative here in the US and very, very new. But in Europe, they've been doing this since the 1990s. And as the project you mentioned, like they are very familiar with it. So they're building the size of their industry, of the mass timber industry is much larger. And also the state of the art of their industry is more advanced than what we have here. So what happened is, and then transportation through boat is fairly cheap when compared with trucking here in the US. So we were able to supply all our timber from Europe, and all our timber comes from Austria. Then it was being trucked to Germany. Then it was put in a ship container. The container was landed in the US in ports either in the East Coast or in Canada. From there, it was put into a train. And then the container was finally opened in the port of Milwaukee, where interestingly, it went through customs there, because otherwise you have to, if you open the container first, you have to pay taxes on every state you cross. And then from the port of Milwaukee, which is like 10 minutes from the site, it was put in a truck and then taken into the site. That said, it worked very well for us in terms of the supply. Like they have a lot of supply there, and the prices are not subject to the big fluctuations of the American market. Now, during the construction of this building, obviously COVID happened. One of the big issues we had was the containers. As you all know, like the whole container traffic in the world has been completely messed up, and suddenly there was a lack of containers. So our suppliers worked day and night to get us the containers that we needed. We had very, very minimum delays during construction that actually they were able to gain back that time because of the speed of construction. So we didn't experience any supply issues. It was tight, and COVID didn't help at all. But we were able to get quotation marks cheap material from Europe and use it in Milwaukee with no problems. So I think for a project in New York, it's even easier because you're even closer to the East Coast, so even easier to get the products from Europe. So always, one thing we do in other projects is we always keep that door open. We have like an American supply or European supply.
Yep.
Let the market decide which material is more competitive.
Oh, it's a great presentation. I can't thank you enough. I don't know if Aniowski Peñamora, who's the director of our CBIPS program, former dean of the engineering school, former commissioner of DDC, is on the call. Any closing words, Fanny?
Thank you, Rick, and thank you, Alejandro. It was a pleasure to hear you, and definitely you introduced the students to a topic that has been a point of conversation for a while, but you are now showing it that you are doing it, and you went through the different steps, both from the design and the construction, as well as now with the question from Rick, the supply chain. So I just want to thank you. As always, we value our relationship with TT. It has been going for a long, long time, and you have been a central source of kind of information and knowledge to every city that we go to. We always find somebody that has that at the T office that we can work with, and your presentation continue to live to the expectations and beyond. So thank you so much for the presentation. And I just have a quick question, Rick, if you have 1 minute.
Sure.
You know, one of the things that normally there is a lot of talk is from the perspective of sustainability and embodied carbon. Did you do any study when you were doing like the assessment of the research project with Cambridge in Chicago, as well as the actual construction of the Ascent in Milwaukee? What was the embodied carbon, particularly when you have that transportation component coming from Austria? Was there any work as part of the research or the justification for using in the project in Milwaukee?
Yeah, so sustainability wasn't the main driver of Ascent. It was more like the use of timber was more like a, and as a, it was attractive of using this material and the experience of the material that was the main driver. So we didn't do many comparisons for this specific project. However, we have done it for many other of our projects. One thing you get with when transporting across the sea is transportation in boats is very efficient when in terms of embodied carbon. So the part that is gonna add more to your embodied carbon is gonna be the truck from the port to the city, or if you're in Europe, typically the trains are electric, so that doesn't add so much embodied carbon. But here in the US, also like the fact that the trains can also have an impact. But the worst part is going to be the truck part. That's where you get like the most embodied carbon. These boats, they are so big, they transport so much cargo that the embodied carbon that you add on that process, even if the distance is very long, is actually not so much.
Thank you, Alejandro. I appreciate it. Again, thank you so much for your presentation. I really appreciate it. And I know the students will gain so much from it. Thank you.
Happy to do it.
And I'll say goodbye and thank you. Hope to meet sometime in person. Take care.
Yeah.
Thank you.
Good to meet you guys.
Thank you.